All right, let's get started. Today we have Qingfeng Lan. He's an MSc student and he's going to tell us about predictive representation learning for language modeling.
Okay, thank you, Abhishek. I'm Qingfeng Lan, and today I'm going to present predictive representation learning for language modeling. And this is joint work with Luke, Martha, and my supervisor, Lorna. So I first do an introduction, and then I'll show you how to transform post-tagging to an IO problem. Then I'll introduce our main method called predictive representation learning, short for PRL, and followed by some experiments. We will draw the final conclusion and show you and also the future work. So first, the goal of our work is to improve language modeling with the help of a part of speech tagging. So here the language modeling is the main task and the part of speech tagging is our auxiliary task. Our basic method is to apply reinforcement learning to language modeling with the help of general value functions. And the goal of language modeling is to predict the next word in a document. And because there are about 1 million words in English according to Wikipedia, and it's very hard to predict the next word from such a large vocabulary set. We use perplexity to measure the performance of a language model, and the lower it is, the better a language model is. And part of speech tagging is relatively easy. It's the goal of post-tagging is to predict the post-tag given word, and because there are only less than 50 post-tags, it's relatively easy. And for current sorter, we can achieve at least 95% of accuracy. It is also strongly related to language modeling, so that the representation can be shared between two tasks. We'll show that how to solve post-tagging with our Q-learning algorithm next. So the basic idea behind this work is quite simple. Let's say we have a large vocabulary set, many words inside, and combine. If we know the post-text or these labels of these words, we can then divide this large vocabulary set into several parts. Say we don't know what the next word is, but we know the post label of the next word. For example, let's say it's a verb, then we can only focus on the verb set and ignore other parts, which can greatly reduce the hypothesis space and improve the probability of predicting the next word. So that's the basic intuition. And then I'll show you how to transform post-tagging into IO problem. So let's say give a sentence, we want to create an MDP, and the state space of this MDP will be the vocabulary set. The action set is the set of all possible post labels, such as pronoun, verb, preposition, noun, etc. And the cumulant is a little bit tricky. When a correct post label, here the label is same as action. When a correct action is chosen for the current word, it leads to the next state with cumulant 1. Otherwise, if you take the wrong action, which means you predict the wrong label, you will get 0 cumulant, and you will go to the terminal state T. And here's an example. I'm using the sentence "I'm going to school" as an example, and the post labels are behind these words. And for example, if I'm in state I, with the correct post label is pronoun. And if I take action pronoun, I'll go to state M with cumulant 1. Otherwise, you will go to the terminal state with 0 cumulant. And here the action value Q is the expected discounted number of steps that a policy will be able to correctly label the next word by taking the action A. And a correct action A usually leads to a larger action value. So to predict the true label, we simply take argmax over all action values. And we then introduce our main math, PRL. And here again, main task is language modeling, and the auxiliary task is post tagging. And since the task of language model is to predict the next word. To coordinate with that, we change the goal of post tagging to predict the post label of the next word without giving the next word. We can't, because our main task is to predict next word, so we don't know the next word. That's why we predict the post label without giving the next word. And PIL is an auxiliary text learning framework. It's also a sequence-to-sequence model. And here you have a encoder, and for each word WT, the encoder encodes it into a word vector E, and the encoder is just an embedding layer shared by all tasks. Then you can concatenate the word vector with T. I call it T is the label trace, which is used to encode all historical labels. You pass this concatenate word vector into the post decoder. The post decoder and the language model decoders here are all RNNs, and the structures of these RNNs depend on the exact models. I will explain that later. And the post decoder, then we will compute the action value of vector Q. It's actually a general action value vectors. And to predict the post label next, we simply take argmax. For this part, the language model decoder is also an RNN, and in this picture there are 3 hidden states. H1, H2 is 3 because there are 3 layers. And after the post decoder produces the action value Q, we pass it to the language model decoder, and then we concatenate Q with H1. We do this because we want to incorporate the information of post tagging into the language model decoder and make the hidden representation more predictive. And finally, the language model decoder will produce the language model output. We then test this PIL with some experiments. We tested on 2 data sets, Panish Bank and Wikitext2. We also combine with PIL with 2 sort models. One is called AWD, another one is called Morse. That's why I say the structure here is dependent on the exact models. So if you are using AWD, you will use the structure of AWD. Otherwise, you will use the structure of Morse. And we do extensive hyperparameter tuning, and we average result with standard errors over 5 runs. I would like to run more, but since training language models is really, really expensive, I just got results over 5 runs. And here the results for 2 models on 2 data sets. You can see that when combined with PIL, the task perplexity is significantly lower for both 2 data sets. And we have similar results for when PIL is combined with Morse. So we can draw the conclusion that PIL improves the performance of language modeling significantly. Later, we also draw the learning curves. And what we found is that PIL accelerates the learning process greatly. Here, the x-axis the number of epochs, the y-axis is the perplexity, and you can see that to achieve the same result for AWD, it needs 500 epochs, but for AWD PIL-Q, it only needs 100 epochs, and we have similar results on Wikitext2. We then studied the effect of post tagging accuracy on PIL. So notice that predict the post tag given the word itself is very easy. We can achieve at least 95% of accuracy. But predict the post tag without giving the word is hard. In our experiment, we found that the accuracy is usually lower than 50%. And this is exactly our case because we want to predict the post label of the next word without giving the next word. So this makes us to ask questions like, what if we can improve the performance of post tagging without giving the word? Will the performance of language modeling be improved as well? So as I said, to to predict the pause tag without giving the word is really, really hard. And the only way we can improve the accuracy is cheating. So we allow the pause decoder to have access to the next word when predicting the pause tag of the next word. And this is clearly cheating because the information of the next word is leaked to the language model decoder through Q. Let's go back to the model structure here. So if you leak the information of the next word to pause decoder, then this information might be leaked to language model decoder by Q. So this is why we call it cheating. But we can see what we want. We can see what if we can improve the performance of pause tagging. And the answer to this question is definitely yes. As you can see in this picture, as we increase the accuracy of pause tagging from 40% to 80%, the perplexity is decreasing significantly quickly. So we can improve the performance of language modeling by improving the performance of pause tagging in this case. Finally, I'd like to draw some conclusions. So I want to say that predictive representation is really helpful. It leads to better performance. It leads to fast convergence rate. And if the main text is too hard, sometimes we can find some useful auxiliary tasks that are helpful to the main text, but easier. So by solving the easier tasks, we can help solve the main text, at least part of it. And for future direction, as indicated in these experiments, the rest we can do is to try to improve the performance of pause tagging for the without giving the next word. That's all. Thank you. Sorry, maybe I'm a little bit too fast. Any questions? Okay, so the discount factor is so generally for general value function for general value functions, the discount factor is also a gamma function. But here in our experiments, we are using a constant number which is chosen from 0 to 1. Any other questions?
Hi, I loved your talk. Thank you. Can I ask, could you frame this also as a supervised learning problem without RL, and what do you think the pros and cons of that would be?
Yes, actually, in my experiments, I also like the result I didn't put here is that we also replaced the action value function with the probability distribution, and we found that the performance of language modeling is also increased, but in that not as much as when we with general action values. So I guess that basically is to approach these two different different representations. Does it answer your questions?
Yeah, thank you.
Maybe I'll just follow up with that. Then I think that question is also coming from the fact that here you're predicting the label of the next word, and so that does feel very naturally like a supervised learning problem. So then what do you think you're gaining then from using action values? Like, why do you think it does? You said it performs better, but do you have any idea why?
I think the first reason is that the language model decoder has the information of pause tagging, and as I explained here, we can reduce the hypothesis space. And the second reason is that the action values not only encode the information of the next step, but all future steps. But for supervised learning, if you use the probability distribution, not only includes the information of the next step, but not the future information. So these two differences will these two different representations.
Hey, Qingfeng. Cool talk. So I had a question about the POS tagging. So actually a couple of questions. The first one is, intuitively it seems that if if the POS tagger was better, it might help with the original task as well. So like your motivation says, it would reduce the space of possible actions that the next word would come from if you could rely on that. And so you, as a sanity check, I suppose you tried giving it the next word and seeing if it improves the performance, and it seems that that is the case, right? So
Yeah.
Did I get that part right? Okay. Right. So the first thing I guess that comes to mind is, so this seems like the planning with the model problem that we have in RL, right? Which is that the model can be reasonably accurate, but you'd probably want to know when you trust the model versus when you don't. So for example, in your case, if let's say with a 90% chance you get the POS tag right, but if you reduce your action space, your word space according to that, you might be losing out because, with a 10% chance you're wrong. So have you thought about how you would kind of incorporate some kind of uncertainty in your prediction of the POS tagger?
Yeah, actually not, but I also observe a similar phenomenon in my experiments. So basically that here I only try one auxiliary task, which is pulse tagging. In my experiments, the result I haven't put here, that I also try combine it with more auxiliary tasks. But as you increase the number of auxiliary tasks, because of the question you just mentioned, the model might don't know when to trust the predictions or not, and sometimes the predictions are misguiding, and it's really hard to combine with more auxiliary tasks while still improve the performance language modeling. So yeah, I think that's a very hard questions, and right now I don't have a good solution to that.
Yeah, it does sound like a hard problem, but yeah, thanks.
Can you say more about what those auxiliary tasks were that didn't help? What were those tasks like?
So another auxiliary task I tried is called name entity recognition. It's basically you assign a name entity recognition label to each word similar to pulse tagging. And when I combine the two auxiliary tasks together with other language model, and if you assume that the model trusts the predictions of these two tasks completely, but since the accuracy of these two tasks is quite low, as I said, it's low, it's less than 50%. And during test, if the model still trusts all the predictions, it will get at least 50% wrong predictions. That's why this makes it hard.
Have you tried a baseline in which, the POS tag of the next word is like 100% accurate and you just, give it to the language model?
Yeah, that's exactly what I showed in the presentation, right? So if you increase the actual projection to 100%, then the accuracy will be very, very low.
Oh, I see. So this is like, so the POS decoder that you have here is not a learned model, but like something which, I don't know, people have built already, which gives you the right labels.
Sorry?
So are you training the POS decoder here, or is it just you're taking some pre-trained heuristic
Yeah, we also train this part. We train these two decoders together. So this part we apply Q-learning here, so we optimize the TDL here, and the post decoders are also trained while the language model decoder is training.
Right. Yeah. So I was wondering if you tried just like instead of training a POS decoder, just assume that you have a Oracle POS decoder which gives you the right label for the next word, and then just maybe then supply it to the language model. Like that would be a sanity check to see if the POS tag of the next word, does that really help with
Yeah, that's right, and that's also I already did that, and I found that then if you get 100% accuracy, then the language model task will be very, very easy, and you have a very low complexity.
Cool. And then was the final graph you were showing that experiment where you like vary the noise you add to like an Oracle POS? Or is here the actual POS tagging learned and you're just tracking the accuracy over time?
No, actually we vary the capacity of the models, and we did this by changing the size of a hidden layer in RNN. So with a smaller size of a hidden layer, the capacity of the model will be smaller, and so also the accuracy of processing will be lower, right? And if you allow it to have a large hidden size, it will record all information so that the accuracy will be very high, like to 90%.
Cool.
One more. Vincent has also have a question. Is return normalized? No, actually we don't normalize. We don't normalize the return, but I think this idea worth a try, because for different length of words, for different length of sentences, the magnitude of return might be different, and so maybe normalizing is a good idea.
Hi. Just wanted to follow up on that question.
Yeah.
So I'm not sure. So I haven't looked into those data sets before. Is it easy to see whether that issue ever comes up in terms of having different length?
Yeah.
Sentence?
The length of the sentence varies from a very small number to a very large number.
And is there any examples like two sentences of different length starting with the same set of words? I mean, is that does that ever come up in the data sets?
I haven't looked at that, but I haven't checked that. But why do you ask this question? Or what do you want to find?
It's about the same issue, right? If you say you're predicting the third word given the first two, and then if there are two sentences starting with the same word sequence, and they might have different length, then the Q value for those would be different.
Yes.
So I'm just trying to brainstorm whether there would be any issue there.
Because we construct a separate MDP for each sentence, I think that won't be a problem. So in the same sentence, the larger Q you have, which means you have you may find a correct action, correct label for that.
Okay, thanks. I'm gonna think a bit more about that. Thanks.
Thank you for your question.
What do you mean you construct a different MDP for each sentence?
So here I'm using a sentence I'm going to school, but and then we construct a MDP for that sentence. So for each sentence, the MDP structure is different, although it can be incorporated into a very large MDP with different transition probabilities.
But then, I mean, I would have thought here that this was the states changing, not the NDP changing. So then you were learning one Q function for multiple MDPs?
Yes. Yeah, I guess you are right. There's only one MDP, but when we get a sentence, we only focus the part that is relevant to that sentence.
The state changes, probably.
Yeah.
So then in the light of saying there's only one MDP, maybe you could revisit the question that was asked by Vincent about lengths being different, I think was the concern.
Yeah, I think it's also a concern. I would like to try to normalize the return, for example, by dividing the length of the sentence.
So how different can the sentences be in length, for example?
That can be 10 to 100, but in practical, you can truncate the sentence to prevent it from it too long or too short.
So for the data set you used, how long was the sentence ranges actually from size 10 to 100?
I didn't do a statistic, but yeah, I don't know. I haven't do an exact calculation, but normally it's between 10 to sometimes smaller, shorter, sometimes longer. But you can truncate it within a certain range.
And this question asked earlier.
I was
you go
yeah,
for it. I was just going to ask the question you asked earlier, which was, what is gamma? You said it could be between 0 and 1, but what was it actually?
Yeah, it's actually selected with hyper-tuning. We cannot decide the best gamma without experiments, and gamma also controls the value of the delayed cumulants present. So if you have larger gamma, it means that you weight more, you weight the future cumulants more.
Yeah, I was gonna ask about that as well, mainly because I was thinking about different horizon. So so the best gamma may be related to kind of the average or maybe the maximum length of the sentences in the data set. But yeah, again, I haven't looked into the data, so I don't know.
Well, why do you think so? Why do you think that the best gamma is maybe related to
the effective horizon, right? So if you discount, you have a lower discount factor, then
I see.
Yeah, okay.
Yeah. I kind of agree with you. Amanda, do you have more questions?
Can I ask you about the tokens? So are you using a full word at a time? I guess a lot of the popular language models like BERT and GPT use subword level tokens.
Oh, we are just using a token level, a language model. But I think you can also combine with maybe the correct level language models. It all depends on which language model do you want to combine with. So you can change the language model decoder part according to the models you want to combine.
Okay, so you're saying the models that you're trying to work with require full words? Is that what you mean?
Yeah. We're working with full words right now because the models we combine, the two most AWS and most we combine, they are using the full words. It's a word level language models.
So, I mean, it seems like your idea of adding this auxiliary task was helpful. It got you further, but it's hard to imagine how you would take that even further. Like what auxiliary tasks? It sounded like the other one you tried didn't really help. And so are you feeling like more auxiliary tasks will not help get further, or are you saying that that particular one was not very helpful, but maybe there's some other ones that we can find?
Maybe I didn't explain that clearly. So when I tried name entity recognition alone, and it also helps, but when you combined two auxiliary tasks, name entity recognition and pause tagging with language model, then it didn't work. And I think the problem may relate to what Abhishek says. The model must distinguish between a good prediction or a bad prediction, and they can't trust the prediction all the time. Otherwise, it may lead to misguiding or some other problems.
So does that mean that you think that there is potential for adding another different task, or maybe not?
Yeah. And I think the key problem for that is that you need to improve the performance of the auxiliary task. Otherwise, it may not be that helpful. So with more auxiliary tasks, you may get more wrong information. So that's why it makes this problem harder.
I'm trying to imagine what would make a good auxiliary task, and that.
Yeah, that's also a tricky part. Actually, you need to choose auxiliary task carefully so that it relates to the main task. Otherwise, it may not be that helpful. So we want to show the representation between auxiliary tasks. If the two tasks are different, then this representation may not be that good.
On the other hand, you don't want them too similar because then they're just bringing the same information out, right?
Yeah, that's why. So we want to
as well.
Yeah, exactly.
What about like predicting the glove vector of the next word along with the point? Like the thing about the part of speech is that there's so few of them.
That's also the advantage of it, because then it will be easier.
Is there some way to formulate it like with more Q heads, like with the Unreal paper? They found that adding Q heads was the most important thing they could do in terms of auxiliary tasks, but I'm having trouble imagining how that would work here.
You mean adding more auxiliary tasks or more Q vectors?
Yeah, more Q heads for auxiliary actions that you don't actually want to take. I just pasted the paper in here. I'm not sure if you already know.
I don't know this paper, but thank you for posting.
But it seems to me like if you, let's say you predicted the word-to-vec of the next word, then that's kind of like the topic. It's almost like a topic vector, because word-to-vec summarizes the types of words around in that part of the like idea space or whatever. So maybe that would be like you're kind of predicting with POS you're predicting the part of speech, and then maybe with predicting a glove or a word-to-vec you could predict a topic that was coming up, and that would maybe give you an orthogonal. I'm not sure what else to do there, but
like how do you optimize this like predicted word vectors? I mean, what other information do you bring to this this model? So I mean, for my case, I use post labels as other auxiliary information to optimize it. But if you predict only the word vectors, there's no more supervised information introduced. Do you want to explain again?
No, maybe I hear what you're saying. Maybe it's like cheating because it's almost like another language model. Is that what you're saying?
Yeah, kind of. But the essential problem is that we need more supervised information to have a better model. And here, by introduce post tagging, I have the supervised information from the post labels. But if you just predict the word vectors, maybe you need a more powerful word, language model to generate to supervise the word vectors you predict. Any more questions?
All right. Let's all thank Qingfeng for the talk.
Okay, thank you everyone. Thank you for the questions.
Hi, Qingfeng. Yeah, that paper doesn't really show very well. I'll paste the. I don't know if you have access to ICML. The slide deck shows a little better. It's on the
Okay.
slide 4 of that one. That's showing.
Application for stable output universal learning.
Yeah, the slide 4 is showing another type of auxiliary task, which is just predicting the hidden state for the next step, and
Okay,
that's
I'll check
seemed like
that.
a very simple thing to add.
Thank you for posting these papers.
Thanks so much. This is an awesome presentation. Thanks so much for sharing.
Thank you for asking questions. Bye.